In this video, I'm going to explore the concept of 1D cellular automata as described by Stefan Wolfram. This is also known as Wolfram Rule 30, where you take a row of cells and you apply a certain algorithm to decide on the next steps when added on top of each other, create really cool visual patterns. Doing this in MaxMSP is fairly easy by using jitter matrices and jit.gen, and it lets you create really interesting combinations and patterns which can be applied on all sorts of audiovisual algorithms. Let's see how this is done. To begin with, let's see what the rules of our game are. Here is a really useful page about Wolfram's Cellular Automata, which is described as the simplest class of one-dimensional cellular automata. Each cell has two possible values, 0 or 1, and rules that depend only on the nearest neighbor values. Meaning that we are going to have a single row of cells. In Max, we are going to represent this as a jitter matrix. And each time we take a step forward in our cellular automata, we are going to be looking at each cell and its immediate neighbors, as in to the left and to the right. So we are going to have three values for each cell. Its own state, which can be 0 or 1 and nothing else, and the state of its neighbors, which again can only be 0 or 1. When we think of it in this way, we have a limited set of possibilities. So let's say all of the cells can be alive, right? 1, 1, 1, or maybe the left neighbor of the cell is alive and the cell itself is alive, but the neighbor to the right is dead. So it's 1, 1, 0, or 1, 0, 1, 1, 0, 0, 0, 1, 1, 0, 1, 0, 0, 0, 1, 0, 0, 0. These are the only possibilities in this kind of setup. And our rule is determining what is going to happen to our cell if it matches a specific configuration here. This rule is called Rule 30. If I scroll a bit down, you'll see there are all these other cool rules that you can yourself apply after hopefully learning something from this video. But in this case, Rule 30 is this. If all of the cells are alive, the middle one to the left and to the right, then our cell in question will be dead. It becomes a 0. The same thing with the second option and the third option, but the fourth, fifth, sixth, and seventh ones are going to equal 1. The cell is going to either stay alive or is going to turn alive. And if all the cells are dead, well, our cell in question is going to be dead as well. So if we apply this rule to our row of cells, and on each iteration we kind of stack the result on top of or below or above the current cell, well, we are going to get a nice pyramid pattern like this. Of course, this pattern is going to change again depending on which kind of rule we apply to our cellular automata system. But that's enough talking. Let's start actually applying things. Now, I'm going to start with a jitter matrix. Right, and I immediately have a few problems. First of all, I have to define my jitter matrix, as in I want this to have a single plane because each cell is going to have a single value. I want this to be float 32 data type, and let's start with 20 cells, right? This is one-dimensional, so it's just going to be a single row of cells. I can visualize this using jit.p window, but of course right now I'm not going to have anything as far as I know. An empty cell or an empty JIT matrix, when it receives a bang, well, it's going to send out an empty JIT matrix, which is visualized as nothing, just complete darkness. But of course, we need an initial position, right? We need at least one cell to have the value of 1. And we can do this in a few ways. For example, I can create a message that says, let me see, set cell 1D, and then the coordinate of the cell. In this case, it's one-dimensional, so it's, let's say we are starting from 0, 0, 1, 2, 3, 4, 5. And then the value of that cell should be 1 instead of its default 0. If I send this message to my JIT matrix and then send a bang, there we go. We have a single alive cell we have created live in MaxMSP. Of course, it could also be interesting to use randomization as well, so I can use jit.noise with the same specifications, so 1 plane float, 32 data type, and 20 at its dimensions. But this is going to give me a bunch of random noise, meaning values between 0 and 1, not 0 and 1 or 0 or 1, but anything between 0 and 1. Here it's visualized as these gradients between black and white. I can simply use a comparison operator to kind of snap this into values of 0 and 1. So jit.greater than is going to apply the greater than operator onto the incoming jitter matrix, and I can use the val attribute to set its default value. Let's make this 0.8. So if the result of jit.noise is going through this, each cell is going to ask itself the question, is my value greater than 0.8? If it is, that cell is going to be 1. If it is not, it is going to be 0. Which means I can get a bunch of random configurations like this as well. Both can work depending on which kind of patterns you want to create, or if you want to have a single starting point or some kind of combination of alive and dead cells that you want to iterate in your cellular automata. In any case, we want to have a starting point, right? So this is going to be yet another jitter matrix, jit.matrix 1 float 3220, but I'm going to give this matrix a name, which should be the very first argument after the object name. And the name can be anything, but I'm going to name it Wolfram because I'm going to be using Wolfram's ideas and algorithm. And I'm giving this jitter matrix a name because I will be using feedback. I'm going to create another jitter matrix also with the name Wolfram, and updating one is going to update the other. But for now, let's start with our current configuration, right? So we have a single cell here, and if I send this matrix to that matrix, well, it's just going to copy the data here into this matrix and then send it out. So essentially we are just copying jitter matrices. Cool. And then I can finally create my good old friend jit.gen, which is where the algorithm is of course going to take place. So this matrix is going to go in, something is going to happen in jit.gen that calculates the next step in my cellular automata, and the result is going to go into jit matrix Wolfram, the very same matrix, creating recursion. Which is all nice and fantastic, but the tricky part is going to be setting up the algorithm. So I'm going to lock dispatch, double click my jit.gen, and let's see what we have here. I think first of all, I should make some notes about the rule that I'm going to be applying. Right, so if I create a comment here, let's see what are my possible states as they're ordered here, right? 111 or 110, 101, 100, 011, 010, 001, and 000. These are my possibilities. And I also have my rule, which is 0, 0, 0, 1, 1, 1, 1, 0. I can even kind of try to get this lined up for a bit better visualization. Let's see. There we go. Now this is a graphic design video. No, it's not, it's still a programming video, but this is what we want to do. So depending on the state of the cell and its neighbors, if it is 111, then give me 0. If it's 110, give me 0, and so on and so on and so on. And that is going to determine how our row evolves in time. So how are we going to do this? Well, first of all, I need my neighbors, right? And that is why I'm using jit.gen, because it's very easy to pull up neighboring cells by using the nearest pix operator, which is going to nearest neighbor sample a matrix. But you might have noticed this pix at the end, which changes which kind of coordinates this object receives. If you have seen my other videos about sampling videos and images in jit.gen and jit.gl pix, you'll know that coordinates usually are expected to be normalized, as in between 0 and 1, regardless of the dimension of the jitter matrix. But in this specific case, with nearest pix, it's expecting pixel coordinates, right? Starting from 0, 1, 2, 3, 4, 5, 6, and so on and so on. And because we have a one-dimensional jitter matrix, it's going to, with a dimension of 20, it is going to go up to 90. So let me create 3 of these guys, right? And the middle one is going to be our current one. So I can get my cell coordinate by using the cell operator. And that is going to go into the second inlet of nearest pix, which is going to receive the pixel coordinate. And to look to its right neighbor, well, I just need to add 1 to the cell coordinate, right? So now the coordinate is 1 higher than the cell that is being processed through this jit.gen algorithm. And similarly, if I subtract 1 from my cell coordinates, well, I'm going to get its leftmost neighbor. Now, in the first inlet, I just need to tell this operator or these operators which input matrix to sample. Well, I only have a single matrix going into this jit.gen object, so just take in one and just sample that matrix based on the cell coordinates that I'm giving you. Now there's only one thing we need to be worried about, which is looping around. So imagine that I am, let's see if I can get it. Yes. Let's say we are working with this very specific cell, right? And I'm looking to its right neighbor, so I'm adding 1 to its coordinate, which is 0. But what happens if I subtract 1, right? I would get -1, and there is no cell here with a coordinate of -1. Well, luckily, the nearest pix operator automatically by default works in wrap mode, meaning that if it receives a cell coordinate that's less than 0, it's just going to wrap around to the end and start counting backwards from there. The same thing is going to happen if I have a cell at the end and I try to look I try to look to the right. Because there is nothing to the right, it's going to wrap around and start counting from the beginning. So in the case of our cells to the left and to the right, they're going to wrap around to find their neighbors. Going back into jit.gen, alright, so I have my values here, and I know that these cells are either going to have the values of 0 or 1. But here's my challenge. I need to get those values and kind of compress them into these numbers. I don't want a list of 1 and 0 and 1 or something like that. I want 111 if all of the cells are alive, or I want 001 or just 1 if the rightmost cell is alive and only that cell is alive. To do this, all I have to do is to apply a bit of mathematics. So I'm going to take the left neighbor and I'm going to multiply whatever value this nearest pix spits out with 100, meaning instead of being 0 or 1, this is going to be 0 or 100. The current cell I am putting through this jit.gen, well, I'm going to multiply its value with 10. And the rightmost neighbor, I'm going to multiply it by 1, meaning nothing is going to happen to that value, but I'm just putting this here for demonstration purposes and to make this algorithm as clear as possible. So now either I'm going to get 0 or 100 here, I'm going to get either 0 or 10 here, and I'm going to get either 0 or 1 here. And if I add all of these values together, I should get one of these possibilities. Here's a neat trick for adding multiple values up in jit.gen or jit.glpix or in the gen environment in Max MSP. If you have a single plus operator, you can simply put all the values you want to add up to its firstmost inlet. And when you run your jit.gen, when you run your jit.gen code or your jit.gen patch, this is going to work. Having something like this is going to add up all of the values together, and from the outlet of this plus operator, we are going to get the sum of this value, and this value. Meaning we are going to get something like this, either 111, 110, 101, 100, and so on. This solves the first part of our algorithm. Right now, I have an algorithm where each cell is looking to its neighbor and is giving out its state in relation to its neighbors. Well, let's check this, right? So I can simply use equal operator to check against each possibility. So equal 111 equal 1110. And what are these going to do? Well, they're going to compare the incoming value with these numbers, and it's going to see if it matches any of these. Notice what happens if I put in 0, 11. It just becomes 11 because that's what this value is. But in our algorithm, this means 0, 1, 1, as in the middle cell is alive, the leftmost cell is dead, and the rightmost cell is also alive. And of course, 0, 0, 0 is going to equal to, well, 0. And here we have a bunch of comparison operators. I'm going to connect the result of my calculation to each of these operators. And what are these comparison operators going to do? Well, they're either going to give me 0 or 1. So if the incoming value, let's say, is 1, 1, 1, this one is going to return 1, and the other ones are going to return 0. Or if it is, let's say, 0, so all of the pixels are dead, well, only this equals 0 is going to give me 1, and the rest are going to give me 0. And because, only one of these can be true. It can't be that this value both equals 0 and 110. Well, I'm only going to get a single value here. And I'm going to turn this into an identifier for the current state of that cell in relation to its immediate neighbors. I am going to multiply the result of these comparison operators with what I call index values, as in times 1, times 2, times 3, times 4, and times 5, 6, 7, and 8. 6, 7, and 8. Once again, do notice that this times 1 is completely redundant. It's not necessary, but I'm just putting it here to make sure the algorithm looks very clear to you or me in the future. Now, what is going to happen in this case? Well, each of these are either going to give me 0 or 1, but it's going to be multiplied by this number, which means I'm either going to get, let's say in this case, 1 and a bunch of zeros, but if this value equals 11, then I'm going to get 5 and then a bunch of zeros. Meaning if I accumulate all these values, if I add these up, what I'm going to get is essentially the identifier of the current state of the cell. Right, so now the result of this operation is going to be either 1 or 2 or 3 or 4 or 5 or 6 or 7 or 8. Remember that it's not possible for more than one of these comparison operators to be true, which means once again I'm getting an identifier for the state of the cell. Which means I can finally apply my rule. I can check what the identifier of the cell is, and then I can input my rule. Let's use a selector operator for this. So selector is going to select between a number of inputs, and it just needs as an argument how many different inputs there are going to be. Well, there are 8 possibilities, so I'm going to have 8 inputs. The first inlet of this operator is going to decide which one of these inlets are going to be forwarded from this outlet, which matches perfectly with my identifier numbers, because if this is 1, then this value, whatever goes into this inlet, is going to be sent out. The same with this, choice 2. If the first inlet receives 2, then whatever choice 2 receives will be sent out, and so on. Now I can manually put in these values, and I kind of will, but I want to set this rule as a parameter. So I want to say param and then rule, so the name of the parameter, and then the values, the default values for this rule, which is going to be a list of 0, 0, 0, 1, 1, 1, 1, 0. Setting this as a parameter will let me change it in my max batch if I want to explore different rules for cellular automata. But in my case, I have my rule, and all I have to do is to unpack this rule by using the Swiss operator. And I can give Swiss arguments instead of numbers, instead of letters, to take apart specific components of the incoming list. Right, so 0, 1, 2, 3, 4, 5, 6, 7. So 0 to 7, 8 elements. And simply sending whatever comes out of this param to here is going to extract a very specific part of that long list representing our rule. Meaning that it is going to choose what is going to happen to each cell depending on its states. There we go, and whatever comes from the selector is the next step for that specific cell, if it's going to be alive or dead, either 0 or 1. And that's our algorithm. We get the neighbors, we add those up together to get a single value representing the state of that cell in relation to its neighbors. We compare that to all of the possibilities and multiply each possibility with an identifier number, adding it all up, giving us a value between 1 and 8. And we use that to drive a selector operator, which is going to choose what happens depending on the rule parameter that we have set, and that becomes the value of this cell. The result is sent to JIT matrix Wolfram, so a matrix with the same name, creating a feedback loop. Each time we send this JIT matrix Wolfram into jit.gen, its contents are going to be updated with the results. Meaning I can lock this patch, and each time I click this is the previous step, this is the next step. you can see that it's creating some kind of movement that does not look too exciting when it's one-dimensional, but to make it look like that really nice pyramid image, well, we can add these matrices up together. To do this, I can use the jit.concat object, which is going to put two matrices together, either top to bottom or from left to right, which is something we can determine by using concat dim. And by default, I believe this is left to right, so I'm going to give it the attribute concat dim 1 to make sure that the addition, the concatenation, is vertical. Now, let's see, here is a matrix I'm going to add up, but I know that I want a two-dimensional matrix as a result, right? Because I want a two-dimensional image, not just a bunch of pixels lined up left to right. So I want to convert this matrix into a two-dimensional matrix without disturbing its makeup. And how do I do this? I create another jit.matrix, 1 float 32, 20, and then I give it a second dimension of 1. So it's actually technically still one-dimensional, but we are kind of specifying that it's two-dimensional, but it has only a single row. So I'm going to put this here, and my final result is also going to be a jit matrix 1 float 32 matrix, but let's say with a dimension of 20 to 50. Why not? So it's vertically going to be 50 rows long. And that goes into the second inlet, so by default this is going to be empty, and each time this jit concat receives this matrix, it is going to add it on top of this currently empty jitter matrix, and then we are going to use some feedback. The result is going to be loaded in this jitter matrix, so when the next step comes in, whatever happened before, it is going to be added on top of that iteration. Maybe this is easier to see if we actually do this. And now we have all of these patterns flowing. Again, it doesn't look very interesting, but I think we can recreate the pyramid by starting from 0. If I, let's see, set all 0, this message to my initial matrix is going to just delete everything. And then I am again going to set a initial cell by using setCell1d. And there we go. Let's see what happens if I click this a bunch of times. A bit hard to see, but here is that little pyramid, which seems to be upside down, which is something we can fix by using jit.dimmap, and then we use the attribute, I believe, no, it's not invert, it is, what is it? Let me look at the help file to remind myself. It is invert. So I'm going to say at invert 0, 1. So don't invert it on the x-axis, but do invert it on the y-axis. And this should give me an image that scrolls from bottom to top. To make this a bit more appetizing, maybe we can increase the length of this initial row, right? Let's make it 200 long instead of 20 long. And of course, we have to make sure all of our jitter matrices then are 200 cells long instead of 20 cells long. And let's make this 200 by 200. Now by default, it's all going to be dead. You can see it kind of glitches out there, creating this interesting image. But I believe that should also be removed if we bang this button long enough or use a metro object. So metro 33. So we are constantly sending bang messages to this process. So it's like it's automatically scrolling. Meaning that now if I set a single cell and then I initiate the matrix, here's our pattern. And now it really looks like that pyramid. Keep in mind that this is only one of the rules that can be applied to this kind of 1D cellular automata, meaning I can change the rule parameter in my jit.gen to create different patterns. Let's do that right now. I'm going to create a new message, so pack, rule, and I had 8 things, right? Let's make them zeros by default, so 0, 0, 0, 0, 0, 0, 0, 0, and this is going to go into jit.gen. What I will do is to create 8 integer number boxes, each representing a different possibility in my cellular automata. These are also going to be zeros or ones. And what if only one of these are 1? And there we go, the pattern has now changed. Right now we are applying a different rule. We are applying rule 0, 0, 0, 1, 0, 0, 0, 0. And maybe we can be inspired by these images. What about, I don't know, rule 110, which is 0, 1, 1, 0, 1, 1, 1, 0. So 0, 1, 1, 0, 1, 1, 1, and 0. This killed our cellular automata, so let's reinitialize this. And there now we are getting these health pyramids, just like how it was on this website here. You might have noticed that the numbers of these rules do correspond to these zeros and ones. It's essentially interpreting these numbers as 8-bit numbers. There is a way of taking this integer number, taking the number of this rule and converting it to these zeros and ones, and I am going to link you to a page that shows you how to do this in the video description. But for the purposes of this video and for the purposes of this patch, I think it's sufficient to change each rule on its own and see what is possible by doing this. There can be a lot of applications to this. For example, taking these patterns and using it to control audio effects or video effects or to generate some events. I think it can be really inspiring and interesting to explore the possibilities of cellular automata. In any case, I hope you have found this interesting and thank you for watching.